All right, we're looking at Chem 129. It's a Monday of week 4. It's a midterm week. It's stressful for me too. I'm not happy about midterms, but none of you want the final to be worth 95% of your grade, so we're doing some exams before the final. I would love it if I didn't have to grade anything but the final exam and that was everything. That's how most of the world does it, actually. But in any case, we got some questions we're going to look at. We're doing some review from quiz 2, and then we got some 3.1 questions. So we'll just do quiz number 2. We'll start with number 2. I'll need some reminders of what the question is.
If a scientist determines the solubility of cobalt oxalate is 2.447 times 10 to the negative 9 grams over 100 milliliters, what would they calculate as the molar solubility in the equilibrium constant value?
Okay. So we've got to get it. Did I write that down correctly? 2.447 times 10 to the minus 9?
Mm-hmm.
Now, all of you might have slightly different values, and that's part of why I did if a scientist is, because like, if I just did the actual solubility of cobalt oxalate, you just look up the KSP and the molar solubility and it should be fine. But I said, oh, we have a scientist who maybe didn't measure it correctly. And so you can't just look it up because it's going to be different than the exact value because the scientist maybe didn't do their experiment very well. So we have to do two things. First, we have to convert the solubility to molar solubility. So I'm going to take the solubility. I'm going to multiply by, I want to get it to liters, so I'm going to say 100 milliliters is 0.1 liters. Right, that will cancel out my milliliters. And then I've got to do 1 mole is a certain number of grams. So I need to get the molecular weight of cobalt.
It's 146.95 grams.
Is that given in the problem?
Yeah.
Or? Oh, that's nice of me. I was about to pull out a periodic table and add things together. So I'm going to take my solubility. I'm going to put this in quotes because the most common mistake people make. Remember, this 100 milliliters is a unit. We don't multiply by that 100. It's 100 milliliters is one thing. That's why 100 milliliters is 0.1. I'm going to cancel out that 100 milliliters that I also didn't divide by. The most common mistake people make is they do stuff with that 100 when it's like a statement, not a particular unit. So I can go ahead and I can calculate my solubility. If I had a calculator handy, you can all follow along. I'm going to do 2.447 times 10 to the minus 9, small solubility, divided by 146.9 is that, divided by 0.1 is that. So I get a molar solubility of 1.665 times 10 to the minus 10 moles per liter. Yeah?
I got negative 9.
Did I do something wrong? No, I think it should be negative 10. 2.447 times 10 to the minus 9. Did you forget to do the 0.1?
Oh yeah, I did.
Okay, yeah. And it's divided by 0.1, so that's going to make it negative 10 instead of negative 9. Yep, there we go. Okay, so that's our molar solubility. Now we have to relate this molar solubility to some equilibrium phenomena. So I'm going to look at calcium oxalate, cobalt oxalate, disassociating to cobalt 2 plus oxalate C2O4 2 minus. If I'm just doing the solubility in water, it's plus x into x. I'm going to have KSP is equal to x squared. That is my x. This value is x. So just that value, 1.66 times 10 to the minus whatever squared, should be my 1.665 times 10 to the minus 10 squared. I get the very silly value of 2.77 times 10 to the minus 20 for my KSP value. Now, is that a reasonable answer? I'm gonna just check the equation sheet. Does this happen to be on the equation sheet? No. So couldn't look it up there, but I'm gonna go ahead and look it up because I don't know if this is reasonable. Now I've seen KSPs this small before, so I'm like, yeah, it's possible. It's a pretty small KSP, but just for giggles, because I'm entertained by these sorts of things, I'm gonna look up the solubility product constant for cobalt oxalate and see what I've got. If I can find it. Cobalt, iodate, tyrosine, copper, hydroxide. I'm not seeing it on that list. That's not my complete list. CRC, that's the one I wanted. I opened up the wrong folder. Let's see here. Is it on this one? Cobalt oxalate. Oh, that is way different. 4.43 times. Oh, that's copper. Sorry. Huh. I don't see cobalt oxalate on this list either. Let's see what Wikipedia tells us. Cobalt oxalate. Inorganic compound. There's many different forms of it. Simple, it's a coordination polymer with a ligand bridge. Cool stuff, cool stuff. No information about its solubility. How funny. Because it does metal complexing, probably. It's a faint pink powder. Well, so yeah, difficult to figure out. But if I look at the other cobalt compounds, a lot of these cobalt compounds are like on the order of 10 to the minus 15, 10 to the minus 29, 10 to the minus 35. There's one that's 10 to the minus 2, 10 to the minus 6. So they're kind of all over the place, but this is not an unreasonable value for a KSP value. The thing that's bothering me right now is just I usually try to make problems that have realistic values in them. So I'm like, did I really just like make random numbers? Where did I get this solubility of cobalt oxalate to do this with? And now I'm like checking a bunch of different places to see if I can find it someplace else. Cobalt sulfate. Oh, okay. So the solubility for cobalt oxalate is given on Wikipedia. I want to check their sources for this since I had so much trouble finding it. But it's the solubility, not the KSP value. I was checking KSP tables. The solubility on Wikipedia is given as 2.69 times 10 to the minus 9. So I probably just did numbers varying around that, but it's also a very difficult KSP to look up. So, good question for a quiz where you have access to the internet. Because if you took the time to try and look at, like, I just wasted, like 10 minutes trying to look it up? I did the calculation in less time than I spent trying to look it up. Okay. Questions about that? So this was quiz 2 number 2. On to number 3. Questions about this? Pretty straightforward. So the thing that messes people up most is the unit analysis, and then realizing that this is the X value at equilibrium. Those are the 2 steps that mess people up. Let's go ahead and look at number 3. And again, I'll need someone to tell me what number 3 is. Someone else, if you don't mind.
It was consider a solution that is made from mixing 0.004 moles of A plus and 0.078 moles of B minus in 125 milliliters.
07 or 007?
0.078.
Was it how many zeros on the 4?
0.044 moles.
0.004?
044. So 0.
Oh, 44. Yeah, I did the wrong thing doubled. 044 and 078.
Yeah. And and 125 milliliters of water. If the AB solid formed has KSP of 7.79 times 10 to the negative 8, what is the concentration of cations and anions in equilibrium using the excess small approximation?
Okay. So this is the problem we did 2 Fridays ago. So like, and before I even say what it is, it's just kind of like, okay, so what the heck do we do here? First logical thing to think about is what hints are given in the problem. You notice I didn't write down everything you said. I just kind of wrote down the things that I already knew were going to be important because I've done this problem a lot. Also, whenever I do problems, I always break the information into 2 categories: explicit information and implied information. This is the explicit. I mix A plus and B minus, certain moles of each, in some volume with some KSP value, right? Those are the numbers that I'm given. There's all of this, and then it asks me to find concentration, right?
Yeah.
Which concentrations does it say to find?
Cations and anions.
Both. Okay, so we want to find A plus and B minus. We want to find the cation and anion concentrations. So I've got my explicit information. I've got the information I'm supposed to get to. There is some implied information in this problem that's not told to me explicitly that the problem assumes I can figure out. Every problem in college has this kind of structure. I tell you where to start. I tell you where I want you to end up. Do you know the steps in between? They do this in English classes. They do this in history classes. They do this in, I don't know, I mean, maybe they do it in poetry classes, but it's like where you end up is more like subjective. I end up in a different place than you because it has a different meaning. And it's just all about oversight. Joke from earlier, sorry everyone. Oversight has 2 meanings that are opposite of each other. In any case, English is weird. So what's the implied information? What's it trying to get us to think about here? Now, we're in the context of a chemistry class. We're in the context of not just any chemistry class, Chem 129. What's the thing that we usually look for when we're looking at problems in Chem 129? There's 2 things we look for, 2 steps we always do. First one starts with an S.
Geometry?
And then starts with an E?
Equilibrium?
Yeah. Right, so we're going to look for those types of things. The fundamentals there are, what is in solution that could react or could have some equilibrium? And we have a hint in the words that I didn't write down. It says if the solid forming has a KSP value. It's telling us a chemical reaction is happening when it says that. There's a solid forming that has a KSP value. Not only that, the KSP value is really small, which means a lot of products are going to, that means a lot of solid is going to be there. So if I look at this, I can look at this in 2 steps. I can do step 1, stoic. I'm adding an anion and cation together. Possibility for a chemical reaction there. KSP value tells us definitely chemical reaction there. All of that thinking was implied. There's nothing that's, I mean, it kind of does say a solid forms, right? So that's even kind of explicit, but it tells you solid forms. So I'm going to have A plus B minus goes to AB. I'm going to have 0.44. I'm going to have, 0.044, 0.078, and 0. This is my start, react, excess. It's a 1-to-1 ratio, so I can figure out the limiting reaction in my head is minus 0.044, minus 0.044, plus 0.044. 1-to-1 ratio, 1-to-1 ratio, 1-to-1 ratio. A plus approximately 0. This is where we run into the trouble with stoichiometry versus equilibrium. This one, 0.034. This one, 0.044. I'm going to label these with moles because if I don't label, I start to get confused about my units. Right? We're switching from doing stoichiometry to doing equilibrium. We need to switch from moles to molarity. And we've got to keep track of which one we're in at which time. Okay, so I'm going to go ahead and then say, okay, I did my stoichiometry. This is approximately 0. Wouldn't it be great if it were actually 0? Then I'd be done with the problem. The concentration of A plus is 0. The concentration of B minus is 0.034. 0.034 divided by 0.125. Right? I just take my volume, my moles divided by my volume. That should be my concentration of the other thing. 0.034 divided by 0.125. We get 0.272 molarity. All I had to do was some stoichiometry. If Gibbs free energy and entropy and enthalpy didn't exist, we'd be done. Of course, what would even make the reaction happen if we didn't have those energies driving it towards products? But, you know, if we were just in 127, we'd be done. 0 concentration for A plus, 0.272 concentration for B minus. Ta-da. But we're given a KSP value. We're told the solid form has some equilibrium in solution. So we know that that amount of moles formed has to be too much because that 0 can't really be 0. Should be close to 0 because the KSP is a really small number, but it's not 0. So I say, okay, what is it really? Step 2, I look at the equilibrium of AB solid going to A plus B minus, where my B minus has a concentration from that leftover stuff. My A plus has that approximate 0. I have my initial, my change, my equilibrium, plus X, plus X. Why plus X? Why plus X? Can I have a 0 on my product side? Can I have 0 A plus in solution, have this be energetically balanced? Thumbs up for yes, thumbs down for no. Q versus K, that's a lot of quiet. Q versus KSP? Like, how do we know which direction this is going to go? Are we going to stay solid, or are we going to break apart to ions? How do we know? This is a 128 thing that we kind of skip over a lot this quarter.
The KSP that we have initially?
We do KSP versus initial concentration. Right? We do Q versus KSP, reaction quotient versus equilibrium constant. Now the catch here is the reaction quotient has the same mathematical form as the equilibrium, except for the equilibrium is at EQ, and the reaction quotient is at initial. So my Q, my reaction quotient, is going to be 0 because I've got that 0A. It's going to be 0 times 0.272. So my Q, my reaction quotient, whenever I have a 0 in the product side, my reaction quotient is always 0. Which means it will always be smaller than my equilibrium constant, which means I'm not at equilibrium. I need to shift at least a little bit towards products to get back to equilibrium. So I have to have a plus. I think the plus is going to be small because I don't know where my KSP value is really small. So I'm not expecting it to do much, but it should do something. I'm going to have an X. I'm going to have approximately 272, and then I'm just going to have KSP is equal to 0.272, that's a weird 7, X is equal to. Right, so notice, and this is the part that I keep warning you all about. When I set up these tables and do the math, and you're like, oh yeah, that's easy. The math part is easy. The setting up the tables and figuring out why are we doing pluses, why are we doing minuses, which direction does it go, that's where all of the important thinking is happening. Once I have this table set up and I say, can you solve this? You're all like, yeah, no problem. It's divide by 0.272. But how we get that setup and why we get that setup, that's the part you need to spend more time working on. What are the words in the problem that point us to the different things we're doing? What are the concepts that are kind of tucked in there? But we can go ahead and finish this calculation part up now. This is 7.79 times 10 to the minus 8 divided by 0.272. And I get my x value is equal to 2.864 times 10 to the minus 7.
Yeah.
Is that approximately 0? Yeah, kind of. Compared to 0.272, yeah, it's pretty much 0. It's not exactly 0. And this is where this is not an example of where this is important. Where this is important, well, kind of problem number 2 is kind of where it's important. There are materials that are toxic down at the micromolar and nanomolar concentrations. Parts per million, parts per billion toxicity. So there are things that at that concentration are toxic. So if you say, well, it's approximately 0, you're like, it's approximately not toxic, but you'll still die. Such a small amount, but still at that level can be toxic. So there are places where the stoichiometry, the excluding the equilibrium phenomena in the stoichiometry can lead to pretty bad consequences because you have these things that are toxic at those low levels. You also have a lot of cases where that's not a problem because it's approximately 0 and there's nothing toxic. It's just you've got, like, if you just want to know, like, how much did I make, that correction is not going to be important for how much you made. Because it's less than, like, that's what, like a 0.0001% error. Doesn't really matter if you're just how much did you make. But if you're dealing, like, I think the reason I bring up the toxicity is because I know a lot of people in here are, like, pre-med, medical, bio type interests. And that's where those levels of concentrations can actually be important. And that should be our A concentration. Our B concentration is approximately the same. I could try to correct it with that X value, but it's still going to be approximately 0.272. We're good. Questions? Are we ready to tackle number 4 that I know a lot of people have questions about? Number 4? Oh,
I have a question for when you do the the mole to mole ratio. What are you converting it to? I guess.
So let's look at this calculation here, and I'll explain with this one here.
Yeah.
Right. And when I do this table form for my stoichiometry, I'm skipping a bunch of units. But essentially, what we've got when we're looking at this is we've got 0.078 moles of B. And I'm subtracting 0.044 moles of A. Those units don't match, right? Moles of A and moles of B are not the same thing. But they're related to each other through the chemical reaction I'm working with. So I can recognize, and this is B minus A plus, I can recognize that 1 mole of A plus is reacted for every 1 mole of B minus, right? Because they've got a 1-to-1 mole ratio. Now, mathematically, this is really boring. I'm multiplying by 1. But it's really essential to the units because it makes it so now I'm in moles of B that I started with minus moles of B I've reacted. Is going to give me an overall, I should give myself space to do the math, that's going to give me 0.034 moles of B excess. So that 1-to-1 mole ratio is making it so I can relate the 2 different materials to each other through this particular chemical reaction because that's what we're working with. We go to a different chemical reaction, maybe it's A plus 2B minus, and then that ratio changes because we're doing a different reaction. But in this reaction, for this recipe, that's the ratio we have.
Makes sense.
Cool. Other questions? Cool, let's move on to number 4. I will say, as we move on to the titration stuff we're doing, it's really easy to get lazy with our mole ratio, because like 90% of the time, the way we set up our reactions is a 1-to-1 mole ratio. And it's really mathematically boring to multiply by 1, so we start dropping that mole ratio. And we can mostly get away with it until like 3 weeks from now when mole ratios come back again. Catches everyone off guard. They're like, oh, it's not 1-to-1 anymore. So I still, even as we're doing our titrations, we're literally during the titration section, everything is 1-to-1 mole ratios. I still write the 1-to-1 every time, just so I keep that habit fresh. And I keep that chemical thinking active in my mind. Which, not to get too meta, but the chemical thinking that you're happening because of chemical compounds in your brain. Always weirds me out when I think about the chemistry of thinking, and I'm like, wait, I'm doing it while I'm thinking about it. Neuroscience, it's fun. Number 4. Someone else want to read this one out? I think it's a long one, but the setup's not too long. It's just a lot of questions.
Okay. The solution is 0.079 molarity in lead and 0.100 molarity in silver. For lead 2 bromide, the KSP is 6.6 times 10 to the negative 6. And for silver bromide, the KSP is 5.35.
Can you give me those KSPs again? That was too slow.
Yeah. First one 6.6 times 10 to the negative 6. And the second one is 5.35 times 10 to the negative 13. And then the first question is asking, if selective precipitation is to be achieved using KBr, what minimum concentration of KBr do you need to begin to precipitate the compound that precipitates first?
Okay, so I assume if we look at the 4 questions, it's like, how much for first precipitate, how much for second precipitate, concentrations at second precipitate.
Yeah.
Okay. Because, and how did I know the questions before you even told me what they were? Well, I wrote them. But also, whenever we had this setup, like, you notice this is, we go through the same kind of like chemical questions of, well, what's there to react, what equilibrium could happen, what's going on. And as soon as I see this, I'm like, okay, I've got 2 cations in solution. They both can react with anions. If I put the same anion in this case bromide, I'm going to have a competing equilibrium. Lead's going to try to take up that bromide, and silver's going to try and take up that bromide. They're going to take up that bromide at different amounts because they have different KSPs associated with them. None of that's said in the problem, that's all implied of like the chemical thinking we have to do behind the setup. So as soon as I see that, I'm like, okay, this is going to be a selective precipitation, like the competing equilibria. Y'all know how I draw this, right? Get that arrow drawn with the different marks and all that stuff, right? So even before I start reading the questions, my brain's already picking apart, like, well, what kind of problems have we done like this before? What kind of chemical phenomena can be going on? Which one would precipitate first? Which one would precipitate second? This is the lower KSP. I'm going to take the square root of this KSP, so it's going to be on the order of -6. I'm going to take the cube root of this KSP, so it's going to be on the order of -2. So I know this one is going to be the one that precipitates first. Why did I do that weird square root, cube root thing? Different charges on the ions means I can't just directly compare KSPs, but I can still do some quick math tricks to compare. And I was doing quick math tricks, right? I know that this is going to be AGBR, that's going to be an x squared. Square root of -13 is going to be like -6 because that's about half of it. Same thing here. This is going to be PB2 plus 2BR minus. That's going to be like a 4x cubed. Cube root of that would be like 6 divided by 3. That's going to be like -2. You could go through the full calculation to figure out which one is lower, but here's how I'm going to do it. So like you could do that thinking, or you could say, hey, I notice I need to calculate the bromide concentration at each saturation point. So I'm just going to calculate both and see which one's lower, which one's higher, and that's going to tell me which precipitates first, which one precipitates second. So I'm going to go ahead and I'm just going to calculate both of them. I'm going to do PB BR2 going to Pb2 plus 2 Br minus, using common ion effect where I've got 0.079 molarity there, and I've got a molarity I'm trying to figure out here. Right, that molarity I'm trying to figure out, I'm going to say it's approximately 0 to start. Then I have my plus x. That gives me 0.079. This gets me to x. Right, that's going to be my equilibrium. I'm adding bromide to get to this equilibrium point. So rather than thinking about it in terms of the chemical reaction that could be happening, I'm just going to find the equilibrium value that I would need to get saturation. This is going to give me 6.6 times 10 to the minus 6 is equal to, oh, whoa, I messed up. Do y'all see my mistake?
Include the 2x.
It's 2x. It's not x. It's a 2 to 1 mole ratio. So that's 2x. That's 2x. And as soon as I went to write down my equilibrium expression, I realized I messed up. So I'm going to have my 0.079. And then I'm going to have that times, and that's approximately 0.079. And then I'm going to have 2x squared here. And for my earlier thinking, I knew I was expecting some like x squared, x cubed stuff. So when I didn't have that, I knew I made a mistake. I forgot my mole ratio. Mole ratios are important. Then I can go ahead and I can solve. I'm going to solve for 2x because that's going to be my Br concentration. Yeah, I could solve for x, but there's nothing in the problem asking me for x yet. So I'm just going to solve for 2x because that is my Br concentration. I'm going to do 6.6 times 10 to the minus 6 divided by 0.079 because it was given in molarity, thank goodness. Square root 9.14 times 10 to the minus 3. I don't know if this is my first precipitation or second precipitation. I think it's my second. But I'm going to calculate the other one so I can know for sure. I think it's my second, but we're going to make for sure right here.
Hey, Professor, didn't you say you could figure out which one precipitates first off after cubing?
I'm pretty sure. I'm like 95% confident doing this calculation will make me 100% confident.
Did you explain how with the square root and the 4x cubed case?
The thing I did in my head?
Yeah.
So it was essentially, I knew the math that was going to come out here, and so I just ballparked it in my head. And I knew the math that was going to come out here, going to Ag plus Br minus. My Ag plus concentration is 0.1. This is approximately 0. I'm going to have plus x. This is approximately 0.1. This is approximately x. I'm going to have 5.35 times 10 to the minus 13 is equal to 0.1x. Right, so I kind of, in my head, I didn't do it all this much, but I knew if this was in pure water, I could take silver bromide, and I would have like x squared is equal to my KSP. So if I just took the square root of my KSP, that would be approximately, that would be the solubility in water. Not going to be exactly what we have because we're not in pure water, we've got ions there, but it gives me a ballpark idea. Same thing with the lead bromide. If I had the x plus 2x, if I had 2x squared times x, that would get me the solubility of lead bromide in water. And I can use that idea of in water to approximate. Now, that's not water, so it's just approximate. That's why I'm only, like I said 95, I'm probably 90% confident. I've got some level of confidence, but I'm going to know for sure right now. Now, this coming out to 9.14 times 10 to the minus 3, I'm like, oh, I definitely think I was right. Because when I calculate this x, if I'm doing this correctly in my head, I get 5.35 times 10 to the minus 12. Right, so what that means, so now I say, okay, that's going to be my bromide concentration for that half of the reaction, or for that half of the competing equilibrium. So what that means is it takes a much, much lower bromide concentration to saturate silver than it does to saturate lead in this particular solution with ions already present. So now...
Actually, I'm sorry, Professor.
Yeah.
So if the charges were the same, you could use the KSP to compare.
You could directly compare KSPs because you're going to do the exact same math. You're going to square root both, you're going to cube root both. Now, that can get you into some amount of trouble if the KSPs are really similar. You can get into some amount of trouble because the concentration is going to dominate if the KSPs are similar. But also if the KSPs are similar, it's going to be a terrible separation because your difference in concentration is going to be really small to get the separation. So I can go ahead and I can draw this now and I can say my bromide concentration is going up. Here I'm going to saturate silver at that really low concentration. I'm going to saturate lead at this much higher concentration. At this higher concentration, my silver concentration is approximately 0. My lead concentration is approximately the same. I should have done no reaction with lead. Right, the whole point of this mark is before I've reacted any lead. And I know this point is the lead because I did my calculation to figure out which is which. In class and in the textbook, when you're looking at these competing equilibria problem, they almost always do it for same ion count. And so they're just like, this KSP is smaller, so you know that one precipitates first. And it's like, well, what about when it's not the same? And so this is ballpark it in your head, and then you can do, since this problem asks us to do both these calculations anyway, might as well do them both. And then once we have the numbers, I'm like, okay, so this is the first answer. That's the answer to part A. That's the answer to part B, right? Before I got these two, I was like, well, what if this is part B and that's part A? What if this is A and that's B? But once I have both of them, I can be like, this one precipitates first, this one precipitates second. This means at this point, my lead concentration is approximately the same, so I can just drop that number in for my lead concentration. My silver concentration is approximately 0. I can't just drop a 0 in there because it's approximately 0, not actually 0. So I say, okay, well, what is it really? How do I figure it out? I have to say, well, it's not approximately 0. I mean, it's approximately 0, but what's the real equilibrium? I default to CL because that's the common example we always do. We got AgBr, solid, going to some equilibrium, going to Ag plus Br minus. For this Ag plus is approximately 0 concentration. Notice our approximate 0 thing has changed now. My bromide concentration, 9.14 times 10 to the minus 3, is now known because I'm doing it specifically at this point. Since I'm doing it specifically at that point, I know the bromide concentration to get to that point, and I know the silver concentration should be approximately 0. Then I can go ahead and I should be careful. Although I just made up a new letter, that's like a THE altogether. It's just I was not looking when I wrote my IN, so my I got messed up. But I should be careful. Now that we're doing a lot of stoichiometry, I did this at the end of the class and I confused a couple students. We should make sure we label whenever we're doing equilibrium. We should make sure we've got our labels so we don't accidentally confuse it with stoichiometry. So be really careful with your label, especially quizzes, exams, asking me questions, because I'll look at something, I'll be like, oh, you're doing stoichiometry, and like it's really easy, like in the process of me trying to help you, I think you're doing stoichiometry, you think you're doing equilibrium. We both feel like we're talking about nonsense to each other because we're working on different parts of the same problem. And it's close enough to each other that it's like we can still talk about the problem, but it's far enough away from each other that we both are confusing each other. So labels, really important. Happens for this problem, all 3 tables we're doing are equilibrium tables. Most of the problems where we do this, we skip the stoichiometry step of like how much silver bromide is made. Because there's some stoichiometry happening here. Almost none of these selective precipitation problems ask about that stoichiometry. They just ask about the equilibrium phenomena. Plus x, x, approximately 9.14 times 10 to the minus 3. And now we can solve. We're going to have 5.35 times 10 to the minus 13 is equal to 9.14 times 10 to the minus 3 times x. The math here is just divide the correct two numbers by each other. That's it for the math, right? The concepts of what's going on here, the thinking of what's going on here is all of the important stuff. And making sure you don't miss your decimal points like I just did. Divided by 9.14 times 10 to the minus 3. 5.88 times 10 to the minus 11. Makes sense. This is approximately 10, so this is almost 10 to the minus 4. No, this is almost 10 to the minus 2. I'm dividing by that. Yeah, that makes sense. X equals 5.88 times 10 to the minus 11. Now, is 5.88 times 10 to the minus 11 almost 0? Yeah. That is on the order of picomolarity. You thought nano was small. This is 10 to the minus 12 is pico. There's Nobel Prizes for attosecond lasers. That's 10 to the minus 15 time frame. You can actually start to see electrons moving at that time frame, like moving between chemical compounds. It's wild. And we're like, yeah, they're getting to that point where they can observe chemical like real-time observe chemical reactions happening, which is mind-blowing to me. But it's an absurdly small concentration. I can't think of many. I don't know if there's anything that's toxic at that level. Like, yeah, absurdly small. Question?
Was it to the negative 12th, not negative 13th?
For the whole problem?
When you said the equilibrium is equal to each other, or the concentrations?
No. Oh, that is coincidence of setup. So this negative 12 is the bromide concentration. I was using the KSP.
Oh, okay.
Right, so this is KSP equals.
Okay.
Yeah, and it's just because these randomized numbers had a 0.1 concentration, the KSP and the bromide concentration point look really similar.
Okay,
So yeah,
thank you.
Little detail difference. Other questions? Again, the hardest part of these problems, I'm going to give a recommendation to everyone who's here and everyone watching. The hardest part of these problems is reading it to what you do. Not the math, not the tables, like all that stuff. It takes a bit of time, you practice a bit, you can do it a bit faster. But I read the problem, how long do I sit there staring at it blankly? Or how many times do I reread it before my brain is like, oh, it's that thing? That's the thing that slows most people down. That's the place where the most difficulty happens. So one of the things you can practice is not doing the problems, but just analyzing the problems. Just doing this first bit of like underlining the words that these words tell me I do this thing. This is the type of problem. Like having two cations and one anion, that's going to be a competing equilibrium. This is going to be that type of problem. And just practice getting through that setup phase. How do I set it up? How do I read a problem? Now, one of the difficulties with that is there's a limited number of questions in the homeworks. So after you read through all of the mastery questions, you can open up the optional homework and read through that. You can open up the textbook and read through that. You can just Google problems and read through those. And the thing that makes it a little difficult is everyone's words their problems slightly differently. Even from the homeworks I've used in the past, which those optional homeworks are things I did in the past, versus the way that LabPal is coded and the way that the question flow works better with that. Like, I word things differently, I have things set up differently. The textbook uses pretty different language, still about the same phenomena, still same ideas. So there's benefit in that, but it's just where do you get the problems to look at this? I encourage you, if you're studying with other people, to have friends find problems for you and you find problems for them. Not necessarily solving through to get the numbers at the end, although you should be able to do that. But if you don't have a lot of time to study, read problem, what process do I do? What's my first setup going to look like? I can do it if I get, like, most of you, if I give you the first setup, if I set up the stoichiometry, you're like, oh yeah, that's easy now. If I set up the equilibrium pillar, you're like, oh yeah, no problem. The setting up is where everyone's having the trouble. To the point where I actually am giving more time on the midterm than I did the online portion of the midterm than I did last quarter. Sorry everyone for last quarter, but why would you watch this? Questions about this?
So just for like the problem, like for A, B, C, D, like, so this last part, so that's
A, B, D, C. Right? C was just done with logic.
okay.
We didn't have to do any calculation for that. It was the concentration of the lead ions in solution. Was that C?
I think that was B.
That was B?
B was, yeah.
Oh, wait, maybe I don't know the questions I'm answering. What was A?
If selective precipitation is to be achieved using KBr, what minimum concentration of KBr do you need to begin to precipitate the compound that precipitates first?
That's going to be this number. Part B?
It's just the
Precipitate second?
the concentration of the lead before the second.
Oh,
So that's just
that number.
Yeah.
C?
The bromide concentration at the point where.
Yeah, so I had my B and C reversed. So that's part C is going to be that concentration. And then part D is the concentration of silver ions left in solution. Does it actually say silver ions left in solution?
Yeah.
Oh, those questions kind of give you hints in terms of the order then. Right? Because it's kind of telling you, like, does it use the phrase left in solution?
Present in solution.
Oh, present. Less of a hint, but like, you know, it's still kind of, the order it did it in, I feel like, is the hint that I didn't mean to give you. Because I thought it would be bromide concentration to precipitate the first, bromide concentration to precipitate the second, lead concentration present at the second, silver concentration present at the second. So like, man, it doesn't matter, right? But all four answers are on the board. We've done all four questions. On to 3.1. Am I still recording? Still recording, okay. I just had this funny thought of people. What I haven't checked my statistics to see how much people are watching these videos. I stopped recording my office hours in 2019 before the pandemic because I was going through. I was actually like used to do video editing after I recorded to cut out like weird blanks and like try to like fix things, and it was taking a bunch of time, and I would do all of that and I would post them, and I'd have like 5 views out of a class of 100, and I'd just be like, this is not worth my time. I've just decided I'm just posting it with all of this. Like, I would cut this part out of the videos in the past and just have the problem solving, and I'm like, too much work. I haven't checked if people are watching, but I forgot what I was going to say anyway. I'm getting hungry. I didn't have my snack before office hours. So. 3.1 number 2, who's got that handy?
Use Ka and Kb values from the equation sheet provided in Chem 3 equation sheet. How many grams of HF must be dissolved in water to create 630 milliliters of solution with a pH of 2.47? And then do not use X is small if you do not need to.
What was that pH you gave me?
2.47.
2.47. Okay, so not lots in terms of numbers. All we get is 2 numbers. That's not a lot of explicit information. Tells us to look up Ka and Kb. So as soon as we know how to do that, we can look up the Ka for HF. It has a value of 6 point something. I've got it right here. What am I thinking? It has a value of 6.8 times 10 to the minus 4. Not explicitly given, but pretty easy to find. Almost explicitly given. tells us not to use exosmol approximation. What the heck do we do? It's got grams of HF in water. What's our hints?
The pH can get you the concentration of hydronium.
Not only does it get us concentration of hydronium, but it gets us high concentration of hydronium at equilibrium. Remember, whenever we see pH, we never measure pH while it's changing, because then the probe would just constantly swing around. We measure pH when it's at equilibrium. If we want to do something to change the pH, we do a chemical reaction and establish a new equilibrium before we measure pH. That's what we're going to be doing with titrations. We have an equilibrium pH. We disturb the equilibrium somehow, we get a new equilibrium pH. So this tells us we're going to be doing something with the equilibrium. It also told us, the other hint it kind of gave us is no excess small. Right? We've only used the excess small approximation when we're doing equilibrium calculations. So that's already kind of giving us a hint in the problem. They're like, hey, don't use this thing, but you know where we've always used it. That's why I'm telling you not to use it. Kind of telling us we're doing some equilibrium calculation. So it also tells us we're putting HF into water. So I'm just going to do that for my equilibrium and see what happens. HF aqueous plus H2O liquid goes to H3O plus aqueous plus F minus aqueous. I don't know this. I'm going to call it a question mark. I'm doing this in water, so those starts at zeros. I'm going to be losing this. I'm going to be gaining this. I'm going to be gaining this. How do I know where to put the minuses and pluses? We did this an hour ago. Wow, it's been a long office hours already. Can those zeros actually be zeros? How do I get them to not be zeros? Take some of my reactant, split it into its bits. That's how I get those zeros to not be zeros. So I'm going to be using up some of my HF to create some H plus and F minus. Is it going to be question mark minus X? Notice I'm not using the X small because it specifically told me don't use the X small. X and X. I'm going to plug this all in. I'm going to have 6.8 times 10 to the minus 4 is equal to X squared divided by question mark minus X. And we are in trouble if we don't know we can get the H3O plus concentration at equilibrium. The H3O plus concentration at equilibrium is X. So I can just go ahead and say X is equal to 10 to the negative 2.47. That's not the answer I'm trying to get. I plug that in for my X values, and I solve for question mark, which is equal to my HF molarity initial, and I can solve for that question mark without the X small approximation. Now we're just doing calculator work. 3.47 negative to the power of 10. 3.3, I gotta write this down because I'm using one of these tiny old calculators I like. Encourages me to write down each math step so I can track my mistakes better. 3.388 times 10 to the, let's just call it, let's do proper things here. 3.39 times 10 to the minus 3. Those big fancy calculators where you can kind of do all your calculations and like all in a row inside the calculator, and then you erase it. Really hard to track your mistakes when you do that. I know these little cheapos cost like 10, 20 bucks. I love them. Not just, I mean, this one in particular, I like the button layout of this particular style. But the reason I love them is because the way it encourages me to write things down and keep track of my work. That's what I actually really appreciate about them. Okay, I've got X, now I've got to do some plugging in. Let me show you a math thing that I'm going to do. Because what most people do when they're solving this is they plug in X, they bring this over, they FOIL it through, then they divide it, then they collect their X, they collect their terms. It's a headache. So I'm going to show you the way I do this math, because the order of operations for your math doesn't make a difference. You'll eventually get to the same answer, but there's easier ways to do it and harder ways to do it. So the first thing I'm going to do is bring this up and that down. So I end up with question mark minus x is equal to x squared divided by 6.8 times 10 to the minus 4. Then I'm just going to add the x across. So I've got question mark is equal to x squared divided by 6.8 times 10 to the minus 4 plus x, and that's it. I find that a lot easier than what I see a lot of students try to do some foiling of numbers and things like that, and it's just like, woof, it's a lot. So I square that, divide by 6.8 times 10 to the minus 4, get 1.68 times 10 to the minus 2, and then just add another 3.39 times 10 to the minus 3 to it, and I get this whole thing is equal to, you notice it's easier for me to punch into my calculator. I'm not doing anything crazy. I get 2.03 times 10 to the minus 2. And if you punch that in for your answer in LabPal, you are wrong, because we haven't finished the problem. We finished the part that we usually do in class, but if you don't keep track of your units, you're not done. This is the molarity that we need to achieve, not the number of grams we need to put in to get that molarity. And the problem is specifically asking number of grams, so we have to do a little unit analysis afterwards. Okay, I can recognize that molarity is just moles per liter. So we were going to say moles of HF per 1 liter. I can multiply by my volume to get my number of moles of HF, and then multiply by the molecular weight to get my number of grams of HF. So don't forget those last steps, get your units to match. I don't feel like doing that. I'm like, oh, let's do it. Times 0.63. That gets me 1.277 times 10 to the minus 2 moles. The molecular weight of hydrofluoric acid is 20. So then I just multiply by 20. And I get 0.255 grams. Unfortunately for this answer, I don't have a good, because I don't make a lot of diluted hydrofluoric acid solutions with a particular pH. I just don't do that very much. I don't have a good scale of like, is that a good amount? 0.25 grams. It sounds reasonable, right? My concentration is down at like 20 millimolar, 0.023 molarity. It's only 630 milliliters. So like less than a gram less than half a gram kind of makes sense to me, but I don't have a good context for like making that comparison. Yeah, like quarter of a gram. Okay. Quick aside. Do y'all know why? Do you know hydrofluoric acid is dangerous or not? It's a weak acid. Ka is 6.8 times 10 to the minus 4. It's really dangerous. It turns out it's one of the only acids that dissolves bone very well. Bone. Bone. Because the F minus can interact with the calcium and essentially rip apart your bones. Also, the F minus is a pretty small ion, so it has a lot of membrane mobility and stuff like that. It's also very reactive. Fluoride ions are pretty dangerous. Yeah, so you can put it's. Why do I know this?
It's good for teeth, though.
It's good for teeth in low concentrations. Yeah, it will like clean. Oh, fluoride. Yeah.
Fluoride ion.
Yeah, in low concentrations, fluoride ion will interact with so the material that covers your teeth is this weird like I can't even remember the word for it. Epitaxy. There's like a material, and it's a relatively complicated like calcium phosphate, other thing, and it's got hydroxide on the outside. And so there's this essentially material that's protecting your teeth, and the fluoride will go through an exchange with the hydroxide. We're going to learn a little bit about that later, and essentially fluorinates your teeth. And once the fluoride's locked in your teeth, like it makes it so the hydroxide could react with acids. So things that are acidic will essentially eat away at your teeth if you have that hydroxide material on the surface of your teeth, which we naturally have. You replace that hydroxide material with a fluoride material, it's not reactive anymore. And so it makes your teeth resistant to essentially acid erosion better. And then, low concentration, your biological systems can deal with it, no problem. Concentrated hydrofluoric acid can be used to dissolve skeletons, though. I don't know why I know that. Random things I've picked up in chemistry. There's probably some show where they did that, and then I had students ask me about it. And
there's Breaking Bad. Sounds familiar.
Probably. But there's actually this British scientist who did this experiment with like drumsticks, like chicken drumsticks, and soaked a bunch of them in different acids to see what would happen. And the hydrofluoric acid essentially it was kind of gross, but in the sulfuric acid and the hydrochloric acid, the sulfuric acid essentially, or it was the nitric acid, essentially turned the meat into this like goopy jello that was like dripping off the bone. It was really gross. I think the hydrochloric acid essentially ate it away so that you ended up with this like white bone left over, and like the meat was kind of cut away from it pretty well. And then the hydrofluoric acid completely the bone and all the meat, it was where it was in the liquid, it was like a clean cut, just like a perfect clean cut. It was wild. But it's not just strong acids, it's strong acids and the fluoride ions. That brings us to number 3. Any other questions about this after my silly aside about acids? Okay. Number 3.
Oh, how's it going?
It's good.
Sorry.
Yeah, okay.
We're
about to do number 3.
Okay, I see. My bad.
No,
This is my first time doing it.
Oh yeah, come on in, have a
Alright.
seat. This is mostly 129, folks, where I'm recording it, but no, you're 124, yeah?
Yeah.
Yeah. Get your question ready. I'll get to you in just a second.
Thank you.
Okay. What is number 3?
A beaker with 489 milliliters of an acid solution with a pKa of 5.63 has a pH of 3.
What's the pKa?
5.63.
And the pH is?
3.
Okay.
I'm asking what the initial concentration of the acid is.
Oh, we just did this problem. I mean, not exactly, but my setup's going to be exactly the same as number 2. Right, so I'm just using a generic HA to represent some acid. I'm going to have HA goes to A minus plus H3O plus. There's some Ka associated with this. That's going to be 10 to the negative pKa. And I'm going to have some initial that I don't know. Zero's there because it's in water. Minus x plus x plus x. Question mark minus x, x, and x. Where I can recognize pH gives me x. Right, exact same thing we just did, worded a little bit differently. But notice, do I need to keep doing the problem at this point? I mean, I will. But after we go through the thinking, after I see, oh, I'm given pH and a Ka value, like what we just did, I'm given a volume. I don't know, I think we don't need the volume for this one. And it's because I think this has part A, part B.
Yeah.
Part C, which I took off of the question, needed the volume. but I thought it was too complicated, so I took it off, but I forgot to remove the volume term. So it's just kind of floating around there. Okay, so can you solve? Give it a shot. Now, we're going to end up with something that looks really familiar. We usually end up getting to something like this. Ka equals x squared divided by HA initial minus x. Where I can actually even replace that with Ka equals H3O plus at equilibrium squared divided by HA initial minus H3O plus at equilibrium. And essentially what we end up with is we've got 1, 2, 3 variables, and the problem's just switch which variable we're doing over and over and over again. This one is asking us to find that guy again. So it's the same as the last one we did.
Sorry, I didn't want to distract you. I was just wondering.
What is like the definition of pKa?
Definition of pKa. So pKa is kind of like pH, pOH, all of that stuff. Oh, okay. Sorry. I noticed the number that said 0 on my recording, and I was like, did I forget to record all of this? I've been live for 0 minutes. I've just been recording. Okay, so pH, pKa, same thing, right? pKw, it's all the same idea. P of A would be the negative log of A. And it's just this negative log function that makes it so numbers are in a more like human scale, right? So pKa of 5.63 is like, for example, I know that acetic acid has a pKa of 4.74. It's just easier for me to remember that than other things. So pKa of 5.63 is a little bit easier to say, and let me just figure out what that is, negative to the power of 10. It's a little bit easier than saying 2.344 times 10 to the minus 6. So we often just report things in pKa to just do it a little bit quicker. So in this problem, we can find the pH to find the H3O plus. I can do this one in my head because the H3O plus is just going to be 10 to the negative pH. So it's just going to be 10 to the minus 3. So I'm going to have my Ka, which I just did and I forgot, 5.63 negative to the power of 10. I'm going to have 2.344 times 10 to the minus 6 is equal to 10 to the minus 3 squared divided by the thing I don't know, minus 10 to the minus 3. Do the same math arrangement that I did last time. So I have question mark is equal to 10 to the minus 3 squared divided by 2.34 times 10 to the minus 6 plus 10 to the minus 3. Right, and that's just the way I like to rearrange the algebra because it's easier for me to punch it in my calculator when I do that. Inverse times 1 times 10 to the minus 6 is that, plus 1 times 10 to the minus 3, and I get question mark, which is my initial concentration of acid, is equal to 0.427 molarity.
Can we use the x is small approximation here?
Probably. 0.427 versus 0.426 is probably fine. We could probably use the x is small approximation here without too much trouble. But we don't need to. We know what x is. Right? And in situations where we know what the x value is, we don't need the approximation. If there's no solving quadratic where like it's going to save me a step. We could do it. Well, what does that end up being? So that just means we missed that plus at the end. So I'm going to have 10 to the minus 3 squared divided by 2.34 times 10 to the minus 6. I get 4.273 instead of 4. I get plus 1 times 10 to the minus 3. Oops, I did. That was bad. Oh, I messed up. 1 times 10 minus 3 squared. I know what I did wrong. I did 10 instead of 10. 1 times 10 to the minus 3, so I was getting like an extra digit in there. Divided by 2.34 times 10 to the minus 6. Plus 1 times 10 to the minus 3. Yeah, so I'm getting like I think I made a typo before, but I'm getting like 0.428 instead of 0.427. LabPal will probably accept either answer, so extra small approximation would have worked here, but we didn't need it. Other questions about this problem? Okay, I'm gonna go ahead and stop recording. I'll